I work for Cake Solutions. Despite the name, we're not a bakery, so we do software, not cakes. And we have the name before cake pattern, so sorry, John Pretty. Outside work, I also work on a side project called Troy. It's a driver for Cassandra DB. And let me show you a snippet of this library. So it allows you to define your database schema inside your code, inside your Scala code. Then you write your queries. The code is compiling fine. Let me do a trick here. Let me do something wrong. Let's rename this column. Compile again. Now the compiler should tell me exactly what's the error. Colon review name doesn't exist in table posts. Now you might say, okay, we are using a macro. You can do anything inside a macro. All right. Let me remove this a little bit. Just get it compiling back again. Can I see my cursor? Yep, and let's go to the other tab. So this is what's happening under the macro. This is what the macro generates. So the schema is written as normal Scala code. Implicit values describes the column has type, blah, blah, blah. And your query is also a bunch of Scala code. Let's do the same mistake here. Let's change this to be camel case, for example. Compile. I should get exactly the same error. Column reviewer name does not exist in table posts. Me here. Now let's fix it again to make sure. So which column we changed? We changed reviewer name. Okay, let's fix reviewer name here to be camel case. Save. Now compile again. The compiler is happy. All right. Enough with Troy. I will today show you how to build this, how to do a similar program using type level programming. Let's go back about a year ago when I was working on Troy. I had a very small problem. I'm writing a driver. I have data that's coming from the database after executing my query. The data is binary. The database gives me on the wire a bunch of bytes. Gives me also some metadata. Tells me what's the row that you have selected. Tells you like integer, ASCII, varchar, the database types. My duty as a driver is to take those information and give my user back Scala types or Java types on the JVM, end, string, whatever. So a naive implementation would be, okay, let's define a codec that has a decode function, takes byte buffer, and gives you back some type, JVM type. So the JVM type is a type parameter, and also I expect to be defined database type, some information about what's the database type that we expect here. We are supposed to create instances of this class for every combination. So for ASCIIs, yes, ASCII, the Scala type of it will gonna be string, and the name of this type, as the database knows about it, is ASCII. I'm also supposed to register this codec somehow, so my system, my driver is aware about it. Then in runtime, when you execute a query, I'm gonna ask my driver, can you give me the correct codec that converts ASCII to strings, then decode my bytes? This is fine, but this is happening at runtime. If I forgot to write this line, if there is no such codec, the compiler will not aware about that. I will know only in runtime after I execute my query. So let's improve this a little bit. Let's make the compiler aware about the types, the database types. So if you want the compiler to be aware of something, usually you don't want to write it as strings. You want to write it as types. So first thing, we're gonna represent all the database types as traits, integer, varchar, so on, so on. Then we're gonna rewrite our codec class to be like that. So is this exactly similar to the one before? But now db type is not string anymore, it's a type. It's a type parameter. Now I will extend and create an instance of this codec class, but I will do it in a slightly funny way. So I'm gonna put the instances inside the companion object of codec. I will show why in the next slide. I'm also gonna create the instance. I don't care about the slide, I can just create anonymous class, anonymous instance of some class, then call it something. I don't care about the name. The important bit here, I'm just gonna mark this instance as implicit. Do the same for integer to int, and eventually all the combinations should have instance defined here. In order to use this codec, I will define a helper function called decode, accept two type parameters, D for database type, S for Scala type, the value BB, the byte buffer, and implicit instance of codec. We'll see how to use this right now. So I use this function as following. I give it only the types, varchar and string, the bytes, but I will not mention the codec. I will not write it myself. What this code means, this implicit bit here is telling the compiler, please go look in my code for instance defined somewhere that's also marked as implicit. So the compiler will tell you, aha, I know what you mean. Let's fetch the instance. Yup, it returns foobar as we have written in the previous slide. Integer to int works as well, but let's define something that's wrong. Integer and string, I didn't define this. It's not a valid combination. So the compiler say, whoa, 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 no, this is not working. This is not compiling. You can't do that. Right, so now the compiler is aware about what instances of codec we have defined. And the term to Google about that to know how this style is, this is called type class. So codec is a type class that accepts two type parameters. So this is the word to Google for. Now the rest of the presentation we're gonna be building on top of that. So first thing, I want to fix something here. I find it very verbose to give the compiler two information, varchar and string. I believe the compiler should be able to only take varchar, then figure out, yeah, the output is gonna always be string. So let's build that. Again, so this is how we're gonna use decode. You're gonna send only the varchar type and figure out the Scala type. Now let's build that. So in order to build that, we need another type class. This one is slightly different. It's accepting only DB type. The Scala type is not here anymore. It's down here in the implementation, in the body of the type class. So think of this as a function. So I want the user to give me input varchar. Okay, so what's here in the input goes into the parameter list of the binding. What I want the compiler to tell me goes to the body of the type class here. So the compiler is going to figure out the Scala type and figure out the codec. Let's implement this. So similar as before, in the companion object of the type class, I'm going to tell the compiler how to create an instance of this type class. This is slightly different from before, so I'm not using implicit val. I'm not telling the compiler, hey, this is the instance. I'm telling the compiler, here is the recipe how to create the instance. So I'm telling the compiler, if you could give me a codec from varchar to string, then yeah, we have a binding from whatever varchar to this Scala type string. Okay? Another instance also to bind integers to int, and to use that, we're gonna redefine decode to accept an instance of binding. Let's use that. So decode of varchar gives me back string, and decode of integer gives me back a number. This is pretty interesting. It's the same function. One time gives me string, the other time gives me an integer. And I, as a developer, have no idea what the return type of this function is. I don't know whether it's string, int, I don't know. The return type of this, if I wanted to write it explicitly, I would have to say it depends. It depends on the input. It depends on the binding. I'm not sure. It depends on the binding. So the way to write it explicitly is to say it's b.scala type. So it's whatever inside the b. I don't know. It's whatever. The compiler figure it out. I don't know right now. And the name of this trick or feature is called dependent type. So again, this is what you want to Google for to learn more. Right, so far, this is the hardest bit in my slides. The next is relatively simpler. So let's switch gears. Let's talk about something else. Let's talk about a new feature in Scala that John have talked about it briefly in the keynote. So when you type string word, the type of this string is string, right? Well, literal, but the type is string. So soon you will be able to specify a more specific type. You can specify type that looks exactly like the string, just word here. So make sure this is the position of a type. This is not a value. This is a type. So I'm telling the compiler this function accepts only instances of this type word. So the only valid instance for this is the string word, the value word here. If we try to send any arbitrary string, the compiler will tell you, wait, no. This is foo, I'm expecting word. So this basically means, away from the feature, but this means, gives me a hint. Now the compiler knows about strings. It could differentiate between them somehow. We could use this combined with our example before and change my decode function to take the column name directly, written as a string, as a type, as a literal type, not a value. So decode post title, I should be able to tell the compiler, figure out whatever type this column is. I don't know, just figure it out. Let's implement that. So again, we need a type class. This time our type class is very simple. It's just a mapping from column name to DB type. Gonna define instances of that. So gonna tell the compiler, hey, post ID has column type integer and post title has the column type varchar. Cool? Now we have our mapping from column name to DB type. Think of it as a type level function, something that maps from something to something on the type level. So we got our mapping from column name to DB type. We already, a couple of slides ago, implemented binding, something that goes from DB type to codec. Now we have two type classes, two useful type classes. We want to compose them together in something bigger. Let's call it column has codec. That should, from column name, give you the codec directly. And this is how to implement it. So to compose two type classes, you define another type class. Call it column codec. The input is column name, and whatever the compiler is going to figure out for us is the codec and all the types we need. Let's define the instance for that, or the recipe for the instance for that. So we're going to tell the compiler for any column name, let's call it n. So first step, please find me column has type instance. Please find out what's the schema type for that. If you got it, now please search for a binding from whatever database type you found and give me back the binding. If you got those two, I should be able to define the column decoder. It's simple, just the types here, the implementation is just straightforward. Now, this pattern of composing type classes, the keyword to Google for to learn more is called lemma. And our example is nice, but it does not work. The reason it does not work, just a very small limitation in Scala, that here the problematic bit column has type. You cannot refer to column has type within the same parameter list. The compiler will tell you, oh, sorry, no, I can't do that. Fortunately, the solution or the workaround is well known. People have solved it already. The way to do it, we're going to trick the compiler. We're going to introduce a new type parameter, call it D for database type. Then we will convince the compiler that D should be the same as column name, column has type.db type. And this is how to write it. This is called type projection. I'm telling the compiler, hey, this is not just column has type. No, also the type parameter inside it needs to be the same as D. Now, since we have a name for this type, we call it D now, I could just say D here. The compiler is happy, code works, I'm happy too. Now, let's put that into use. We will have to redefine our decode function. Gonna accept column codec this time. Using it straightforward. You put the types as literal types. Here, the compiler knows about our schema now. Now, let's build on top of that. This is the last bit of improvement in our presentation. So the last bit, I want to select multiple columns. You usually don't say select X. You say select X, Y, Z, right? So I want my decode function to be able to accept arbitrary type parameters. So this is not valid syntax in Scala. You can't just define like arbitrary type parameters, unfortunately. But there is solution. There is a library called shapeless. It has a feature called HList. I guess it have been introduced already. So HList, basically, you type in a list that's similar to the Scala list, but has like this extra H here for heterogeneous. This allows you to put inside the list types that are not from the same types. And the compiler will remember what's the type of every member in this list. This is cool, but if you looked into the left-hand side here, this bit, for me, this is a list of types. This is just arbitrary number of types. Int, string, boolean, can go on as much as we want. We should be able to use this in combination with our decode function to write something like that. Decode post ID, post title, whatever columns you want, and the compiler should figure out how to decode the bytes and give you back an HList of values. Sorry, not drunk. I don't even drink. So let's implement that. We're gonna need another type class, row decoder. The input for this type class is column names. This is HList of literal types, as we have seen before in the previous slides. The output is HList of Scala types, and the decode function should be able to take bytes and give us the HList of values. Let's define the instance. So typically, if you are outside type level programming, in normal programming, if you have a list, a typical pattern to write programs is to do recursion. You split the list to head and tail, do something on the head, then call the function again, do recursion on the tail. Right? This is a very known pattern, and type level programming is no different from that. We will also do recursion. So first step in recursion, we need to define the base case. So our base case, if the column names is empty, if you are not selecting anything, just an empty list, This is simple. The code function doesn't need to do anything. Just an empty list as well gives you back an empty list. On top of that, we will define the cons instance. So what if the list is not empty, if it has one or more elements? We will have to split it to head and tail, and the way you split it, we define two names, head and tail. We know the tail has to be in HList. We're gonna define here our type as that, so it's head cons tail. And I'm gonna ask the compiler, please find first an instance of column decoder for head. If you find it, please look for instance of row decoder, the same type class. So here's the recursive bit. So look for the row decoder for tail. So the compiler should keep looking from this instance over and over, splitting the list till it reaches the last bit, the HNL. Now here we have our base case where the compiler finds the instance and, okay, here's your row decoder instance. Let's use that. So we'll have to redefine our decode function as normal. We're gonna use the new type class, and the implementation is just straightforward. And using this just works. So you get back the HList the same order as you have written in the input. So far, I'm able to tell the compiler what's the columns I'm selecting, give it a bunch of bytes, and it figures out how to decode that based on the schema. So this is basically the first step to draw an owl. So now I will go quickly into the rest of Troy, what's the main features, just really quickly to finish in time. So the result solution, I had to define a bunch of traits to be able to represent a complex or complicated select statement. So things like asterisk. So selection is either asterisk or select clause. Select clause has the type parameters, the columns, the list of strings we have seen. From the table is a string. Where is HList of something called relations, not in the slides. Limit is option of none. Again, the number here is literal number, so literal type. So this is either like sum of 5 as a type or none.type. So everything is a type, there is no values. And to write a query like select XYZ from test, so here you write it, XYZ, table test, and the where clause relation, X equals something, Y equals something. Now we have our query, we have our schema as we have shown before. So table exists, the table called test, column has type test. Inside test, there is column called X, has type db text. So this is the two information I gave the compiler. Here's your schema, here's the query. Please work out between those two bits. So the compiler is able, from those two bits of information, to tell you, hey, Q, the query, has this type. It's a function, takes string int, then gives you back sequence of rows. Every row is basically string int and sequence of string based on the schema. So the compiler figures out that by themselves. Now, I don't want my users to type in this gibberish themselves. So I provide on top of that a macro using Scala.meta. So this is really just very thin macro that parses the string, then gave you back Scala meta tree, so Scala code that should have been written in the, so this is what have been written before. Small problem here, just here. There is a small problem with macros that looks like that. So here the IDE, if you're writing that, it doesn't really know the signature of Q unless it executes the macro. And this confuses the IDE a little bit. So we need to keep away from this style of macros. We need our macro to be able to promise the return type without executing it. So the workaround is I'm gonna ask the user to define case classes that represents the input. So here search X and Y, result your case classes. And here you're gonna tell me in the query what's the input type you want and what's the output type you want. Without executing anything, I can promise you initially a function from search to future of sequence of results, right? But then the macro is gonna generate similar code as we shown before. Also, shapeless has a feature called generic that's able to convert automatically our case class instances to HLists that's similar to it. So I could generate the code for you. This code might not compile if you wrote something wrong, if the search doesn't look like this question mark, so you can still have compile time error. Maybe the IDE will not show you the red underline or something, but eventually you'll show it when you compile. All right, so I have 10 minutes more. I guess I can show a bonus slide before questions. So bonus error messages. So I have shown you in the beginning when I wrote select X, blah, and Z, or wrote something wrong. I got an error that says column blah does not exist. So I knew exactly which error. So Scala has some sort of means to tell you customize the error messages. So it has something called implicit not found. If you put this next to the type class, it will show this your custom message when the instance is not found. But this does not work with our use case. And I'll show you now why exactly it doesn't work. Let's first understand what the compiler does behind the curtain. So when I ask the compiler for an implicit instance for row decoder of X, blah, and Z, it has to search for implicit instance of something. So based on my code, it has to search for instance of column decoder of X and blah and Z, 3 instances. But column decoders also depend on another type class, which is column has type. So it has to look for X, blah, and Z. Those are the ones that have the instances, the schema definition. So first thing, it will go search here, 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 find the instance. Okay, correct. Let's go back. Let's go back. Here, blah. Okay, let's search the instance for this. It will not find the instance because it's the wrong column. So, okay, this is X here. This is a dead end. It will go back. Okay, this is also dead end. We couldn't find an instance for that. So it will propagate. Now we know that there is no instance for row decoder, but we forgot all the details, all the small type classes in the middle. We forgot about them. You only get back information that, hey, there is no instance for row decoder, not specific column. The compiler is going to help me, not going to help me, not going to say this specific type class does not exist. So the workaround that, I decided not to depend on implicit not found at all, not depend on this. I will make sure that there is always an instance for my type class. How is this possible? So column has type is very optimistic. It promises you DB type if you have a column name. So we're gonna change that. We're gonna be optimistic. We're gonna say the output is an either. On the right-hand side, if we are lucky, the happy path is gonna be the database type. The unhappy path is gonna be some sort of error message written as HList. I'll show you now. Now, when I define my schema, I'm gonna say column type, post ID has a column type, right of DB integer. So again, everything here is a type. And the error message, I'm gonna define it in a slightly funny way. So I will put in the companion object of the type class. So the companion object is the last place the compiler looks for instances of your type class. So I put a low priority recipe or instance that says, all right, so for whatever column you have C, called C, So there is an instance called colon has type, and the type output is a list of error message defined in this funny way. So this is a literal type of HList of literal types. Colon is a literal type, is a string. C is whatever input you have and not found. I still had to do some macros to be able to concatenate this error message and show you the error message in a nice way. So details, the more the details is open source on GitHub. So there is github.com/schemasafe/toy. This is like a small version of Troy that's only focused to pitch the idea, no more advanced features related to Scala. Finally, if you want to learn more, this is the book I used to know the details of type-level programming, and shapeless talks about various things I have introduced here. This is a talk in Scala days that have inspired me to do this style of programming, and the exact word that inspired me is, we have at the compile time prologue. You can type prologue program that runs at the type level or runs at the compile time. So basically, we have written today a prologue program disguised as Scala code. Finally, I'm writing, but I'm very lazy, but I'm writing a series of blog posts under my employer's blog, Cake Solutions. So it's called Introduction to Type-Level Programming. I only wrote one part, but there's still more in the pipeline. And who has the first question? I'm give him spinner. Hello.
Hi, thanks for your talk. The library seems pretty interesting.
Thank you.
I have one question.
Yeah.
You said that you provided that SQL-like interface so the users wouldn't have to worry about types and signatures. But I wonder, would the users be able to use directly the methods without type-level Scala compiler? Because I'm not sure that literal types are supported in the Lightband Scala compiler.
Yeah. So literal types, there's a pull request against type-level programming. So it should be merged soon. I've checked the PR, like there is no, like nobody said, hey, no, you cannot have that. So people are happy about it, but it has not been merged yet. So I guess it's just a matter of time. I believe also it's still a way to do the same without merging the feature. So literal types is already in the compiler, but there is no way for the user to write it themselves. I can still, using shapeless today, using the current feature, to do like some ugly code that gives me this literal type. Just the slides will be unreadable.
Awesome.
Yeah.
I just want to say, I don't think it is that horrible. You can, for example, in your decode method where you had a string in square brackets.
Yeah.
Naughty John.
Where you had the string in square brackets, you could replace the square brackets with parentheses, and you can infer the literal type from that. You'd need to change the API, but
Yeah.
you might also need to build a function for composing your HLists from literal types. But I think everything is there for you to do it and have a very nice API as well.
All right. Thank you.